Good afternoon, everyone. Thank you all for joining us today for the SANCOLD Young Professionals Forum webinar on the basics of water resources planning. My name is Ashley Kutsia, and I'm the YPF chair at SANCOLD. It is my pleasure to welcome you all to what promises to be an informative and engaging session, especially as this is our final webinar of the year. I want to thank each of you for your continued support and enthusiasm throughout this series. Today, however, we have the privilege of hearing from Gerald de Jager, a highly accomplished expert in water resources planning. Gerald brings over 25 years of international experience in the field, with specialization in areas such as water resource and hydropower infrastructure development planning, risk-based water allocation, drought management, long-term hydrological modeling, and climate change adaptation. His extensive portfolio spans projects across South Africa, Botswana, Eswatini, Kenya, Lesotho, and many other countries worldwide. Gerald is also widely recognized as a leading trainer and technical educator, contributing his expertise to public and private institutions, universities, and professional bodies throughout Africa. In addition to his project work, Gerald serves on the management committee of SANCOLD and represents South Africa on two ICOL technical committees, one being engineering activities with the planning process for water resources projects, and the other being climate change. His wealth of experience and dedication to knowledge sharing makes him an ideal speaker to lead today's discussion on water resources planning. Before we begin, here are a few quick housekeeping notes. Your cameras and microphones will be disabled during the presentation to minimize any background noise. Questions can be submitted in the chat, and then at the end during the questions and answers session, you can raise your hand and ask your question directly. The session is being recorded and will be shared with all participants after the event. So without any further ado, please welcome me in joining Gerald de Jager. Gerald, thank you so much for being with us today. The floor is yours.
Ashley, thanks a lot. Just checking my sound here.
Yes, I can hear you.
Okay, I think I still got an echo here. How's that?
Sounds still okay. It's a bit of an echo, yeah.
Sorry. Apologies. How's that?
Yes, that's better.
Let me try something else.
It's working now. Sounds good. Just share your screen.
Yeah, I was a little concerned about the echo hearing there. I think maybe we'll figure that out. We were just doing this before we joined everyone, so we're still not quite there. Okay, I'm sure this is fine. So Ashley, just give me the thumbs up and I'll get going.
Okay, if you can just share your screen, I don't see it yet.
Right, how's that?
There we go. Good. You can continue.
Good to go. All right. Ashley, thanks so much for inviting me to present today. For me, this is obviously always a great honor to be a participant in the activities of SANCOLD and in particular the YPF. So congratulations on your successful year so far, the webinars and so on. And hopefully there'll be a lot more in the future. Thanks for that and for promoting SANCOLD and the work that we do as an organization. So what we're going to talk about today, as Ashley mentioned, is the basics of water resource planning. This is the sort of stuff that I'm involved with, and I've been doing this for a pretty long time. And I enjoy sharing it with people. I feel passionate about this, and I think it's really important, and I think everybody will agree. So we're going to try and keep it as simple as possible. I've been simplistic, if that makes sense, in what we're going to do today. There's time at the end for Q&A, as Ashley said. So please write down those questions, make them easy ones. So try and make me look good would be great. And we'll get going. So for starters, we're going to start here. And what I'm going to do is I'm going to try and sketch this whole thing as a bit of a story for you. And considering the fact that this is a SANCOLD event, I'm going to try and make this as relevant as possible for someone who's interested or involved in dam engineering, or dam design, so that this adds some value to your daily life. But what I'd also like to explain to you and make clear in the session is how important water resources planning actually is, in particular when you are in the process of designing infrastructure around water resource systems and designing dams and sizing dams and so forth. So we'll touch on that towards the end. But where we're going to start here is with a very simple water resource system, and it might look something like that, where you've got a catchment area and you've got sources of water here and there, and in addition to that, you've got things using water, and you've got infiltration down into groundwater and so on. So this is a bit of a dynamic system. Let me grab a pointer so it's easier for you to see what I'm talking about. So these systems are dynamic and they can be quite complex. But what we can do is, when we look at a system like that from the perspective of a water resources planning exercise, ultimately our objective is something that actually pretty simple if you show it like this. But in essence, this is exactly what we're trying to do. We are trying to balance resources and requirements. Or the way that I like to often put it is, resources is how much water I can get, and on the other side, how much water I need. Now, obviously, when we're in a situation where the amount of water that we need is more than the amount of water that we can get, then that system is not in balance. And fundamentally, this is what we are trying to achieve in this thing that we call water resources planning. Now, you might be asking, how does this involve me? Well, it involves you very directly. As I said, if you are in the dam design environment, or you're involved in that in any way, how much we need is very much influenced by balancing storage. And obviously that means by the building and the management and the operation of dams in South Africa. So the South African government is one of the biggest dam owners in the world, and I'm sure you know that stuff. But this is really important then from that perspective, is how do we actually size these dams? How do we even know that we need a dam? But before we go there, I think it's something just to consider, looking at this very simplistic picture on the screen here. If our system is not in balance, if how much we need is actually more than how much we can get, the very, very simple way of resolving that imbalance is to increase how much we can get, obviously, and that generally involves building infrastructure like dams, interbasin transfer schemes, that sort of thing, to increase how much we can get. That's sort of option A, if you like. Option B, which is generally the better option, is to reduce how much we need. That's better for various reasons, but that could involve things like water demand management, physically reducing our requirements, or eradicating invasive alien plants, things like that. The sorts of things that reduce how much water we need. Generally speaking, that is always better to try and do that for a number of reasons. One of the reasons would be that reducing our water requirements, generally speaking, is cheaper than building big infrastructure. Not always, but generally speaking, that's the case. Almost always also, it is quicker to reduce water requirements than it is to develop large dams. You know better than I do how long it takes to design and to construct and to commission large dams. We're talking, and the planning around that, obviously, we're talking decades, not so much years. So this stuff takes long, it's expensive, and also very fundamentally, reducing how much we need is more sustainable. So with that in mind, let's look again at our little simple system within the context of uncertainty. I'm going to explain exactly what I mean by that in a moment, but you can see that uncertainty is written on the screen here 3 times, so it's clearly very important. This balancing act that we are talking about seems at face value quite easy to do, but in fact it's not easy at all, because there's a huge amount of uncertainty in the environment that we work in. In fact, it is fundamentally uncertain. Let me show you what I mean by that. If we take the same little system that we spoke about before, we say, well, let's say we want to irrigate, we want to use some water here for whatever reason, and we can delineate this catchment that relates to a point of abstraction over here. We can measure the flow in that stream. We know exactly how to do that, and we can monitor that stream flow at that point over a long period of time. That's not difficult to do. Once we've done that, we can then quite easily plot what we see, and we could come up potentially with a plot that looks like this one. We've got time on the x-axis, we've got available flow on the y-axis. Now, when we take the data that we get from monitoring flow at that point and plot it onto this graph, it might look something like this. Now, before I even proceed, you can imagine that if I monitored the flow in some other river, I would get a different plot. If I monitor not the first 10 years that I've got here, but if I monitor the next 10 years, then that period of data will look different to the one that you've got plotted on the screen. But be that as it may, let's say we focus purely on this specific period for that proposed abstraction point. Then when you look at that graph, the first and the most obvious thing that you can see is that the flow is not constant. Now, I know that we all intuitively know that, right? But looking at it on a plot like this is quite good because it actually illustrates how extreme that can be. By the way, these plots are not made up for anything. These are actual flows measured in an actual stream somewhere. So this is real. But the first thing you can see is it's not always the same. And inherently in that, there's already uncertainty. What that implies is that if we plot it for the subsequent 10 years, we will get different numbers and the plot will look different. And to add to that, we cannot predict what the flows will be in the next 10 years. We could have some idea of the basic characteristics of the flow because it's a function of the hydrology of this catchment and so on. We understand that, but the actual flows we cannot predict. It is fundamentally uncertain. Why? Because it's driven by rainfall, which is fundamentally uncertain in the same way. So now looking at this, first of all, the flows are not always the same, as we said, but in addition to that, we can see some sort of pattern, right? And I'm sure that most of you picked that up already, but there is a very pronounced seasonal pattern here. You can see that there are, if these are years, right, you can see that there are quite clearly dry seasons. So every year you have a drier period, those dry seasons, and then you also have a wet period there. So that would be the wet season where the flows are high. That seems quite obvious, and I'm happy with that. So we can see it. But in addition to that, to make matters a bit more interesting, yes, we have dry seasons, we have wet seasons, but not all dry seasons are created equal, right? So here we can see a pretty severe, pretty dry season, as opposed to this one, which is a wetter dry season. There's a dry season, and there again is a wetter one. So you see, even within the seasonality, there is a lot of variation and hence a lot of uncertainty. You can't really see a pattern there. And similarly, the wet seasons, you've got some wet seasons like this one, and that one in particular here, that's a lot wetter than some others. This is a particularly dry wet season. So I think you can see the variability here and how that underscores this concept of uncertainty that we are faced with when we do planning. Now, this is a basic reality of the world that we need to cope with. Okay, having said that, let's say we can do some statistics on this flow series, and we can calculate, for example, the average flow, which in this case, the monthly average flow is about 7.5 million cubic meters per annum, if those are the units. So this is 7.5 units. And we say, okay, so this is how much water there is available in the stream at that point. That's great. Let's say, for example, we have a target abstraction of 5 units. So the average is 7 units, and the target is less than that, which is 5 units. Now, what I've seen in the many years that I've been involved in this sort of exercise is people often look at those two numbers. They say, okay, the average is 7.5, that's how much flow there is, and the target abstraction is 5. Therefore, we have enough money, we have enough water to supply the target. What they are implying is that the flow in the river is not variable. And this quite clearly shows you how that approach is fundamentally incorrect. So using averages to do water resource planning will result in the wrong answers. Let me show, for those of you who don't know what I mean, what the implication is of that approach. If we just simply take the water that's available there, we will not always get that water. That red area at the bottom shows us how much we will get. And why this happens is because the flow is variable, and in some periods when, yes, we have enough water, we tend to have too much and we can't utilize it. And then in other periods, we don't have enough. Yes, the average is high, but we have this variability causing this problem. Now, this is not new to me or to any of you. Everybody knows this reality, but this is just to illustrate, first of all, don't use averages to do planning. You can see that it's wrong because there's variability in the flow, not only seasonally, but also from one year to the next. And in addition to that, this quite clearly illustrates to those of you who aren't really in the dam design environment why it is that we actually need dams. It is to be able to store this water when we have too much of it, so that later on we can use it when we don't have enough. Okay, with that having been said, before I carry on to that slide, what we call this is temporal variability. Tempo means time, and we call this temporal variability. And this temporal variability is pretty pronounced in specifically catchments where it's arid. So the more arid our catchments become, the more pronounced this temporal variability tends to be. So the bigger the peaks and the drier the dry periods, and also the longer the dry periods. Now, you can now, just looking at this picture, you can imagine that the more variable it becomes, and the bigger these peaks are, and the longer these dry periods are, the less water I actually have available to me. And you can almost start to intuitively expect that to be able to utilize this water, the more variable it becomes, the bigger my dams need to become. I'm going to show you later that that is in fact the case, but you can almost anticipate that by simply looking at this graph and thinking about it logically. So this we call temporal variability, more pronounced in arid catchments, and unfortunately, because most of our country is arid, this is a specific challenge in South Africa, and where we have very high temporal variability in almost all of our catchments. There are exceptions, but in addition to the temporal variability, we also have a lot of spatial variability in the distribution of our water resources. This is a map of the country that I'm sure you've all seen many, many times, but we're looking at mean annual precipitation in millimeters across the country, and you can quite clearly see the pattern here. You've got wet eastern regions generally like that, and you've got some pockets that are very wet as well here in the southern areas of the Eastern and Western Cape, and then also in the Western Cape Mountains over here. Now, just looking at the eastern part of the country and plotting this red line, that's basically the Drakensberg here, or the escarpment, if you like, running all the way up to the north there. But quite clearly, it's wetter on this side and drier on that side. And I think most of us understand why that happens. That's a whole nother discussion. But if you look at rainfall and the distribution, it looks like this. But when we then convert that using our clever models and whatnot, because we understand how rainfall becomes runoff, we can also generate a map of mean annual runoff depths. So this is also in millimeters, so to make it comparable to rainfall. So that is what it looks like. And you can see that the map looks similar, but these this spatial variability that I was talking about becomes even more pronounced, where the wettest areas are now very, very much limited to these eastern mountainous areas and Lesotho, and then again these areas in the southwest and south. So we had these two challenges that when I say there are challenges, I'm not exaggerating. This makes it very difficult in South Africa to actually manage our water resources. We've got high spatial variability that you're seeing on the map now, and we've also got high temporal variability in hydrology. Now, looking across this divide here, in the more arid catchments, that temporal variability becomes more pronounced, and fortunately less so on this side of that divide in the wetter areas. So those are our two biggest challenges. There are other challenges as well. if you look at our simple little water source system that we spoke about when we started, this is maybe what this one looks like, but in reality, systems are actually a lot more complex than that. I mean, even this is not really representative of how complex these systems can become. The Vaal River system, the integrated Vaal, is probably one of the largest and most complex interlinked water resources systems in the world. It's very, very difficult to manage something like that. Not only is it complex in its connectivity, like it's suggested here, but also in the fact that it is so spatially large. It actually includes many different climatic regions. And that's very difficult to manage, clearly. So that's the third challenge that we've got. And even with that, we've got more issues. And I can probably come up with a massive list here. That's not only 4 things, many issues in South Africa and many other countries actually around managing water resources. So here are some of them that I think most of you are familiar with and you've probably experienced yourself personally. But I'd like to quickly elaborate on that one at the bottom. What do we mean by monitoring? So monitoring can relate to many things within this space of water resources planning. But the most important thing that we need to monitor is rainfall. Rainfall is the basic source of the water, of the surface water that we use in this country. And if we don't know how much rainfall we've got, then it's very, very difficult to actually manage this whole thing. So I wanted to show you this because it's interesting. And you may have seen this graph before, but what you're looking at here is rainfall monitoring in the whole of South Africa. We've got a time axis on the x-axis here, and from 1920, in this case, only up to about 2015 or so, which is when this graph was updated. This is from the Department of Water and Sanitation. But what you're looking at in the y-axis is the number of stations, of rainfall stations, that were actively monitoring rainfall at that particular date. So you can see in 1920, the South African Weather Service had over 2,500 active stations in 1920. It was a very long time ago. That in itself is actually pretty interesting. And that they then commissioned more and more rainfall stations up to about 1940, 1950 or so. And then their network started to decline pretty rapidly all the way through. And that decline just keeps going all the way to here. That's not good news. Currently, we don't have enough rainfall stations in South Africa to do proper water resources planning. Fortunately, the Agricultural Research Council, they also have some stations, and they remain sort of stable since the 1980s up to today. And then very importantly, DWS themselves also monitor stream flow, specifically at their dam sites and so on. So, monitor rainfall at their large dams and so on. So we've got DWS ones as well. And they're actually becoming more and more important with the decline of the weather service stuff. This is a horrific situation, and if you're not scared when you look at this, then you, I think, missing the point here. If we don't have rainfall data, we cannot manage our water resources. And the reality of this graph, if you look at it just simplistically in its current shape and form, there are fewer stations open today in South Africa than we had in 1920, and that's a problem. So with all of these things being said, I spoke about the uncertainty in rainfall and that resulting in an uncertainty in stream flows, also high variability in stream flow, and also spatial variability in the uncertainties around that. We can actually even add climate change onto all of this, which adds an additional layer of uncertainty that I haven't mentioned before, but that's going to be a short to medium and long-term reality for us, which is an additional uncertainty that we're going to have to manage. But with all of that having been said, it's sort of starting to feel like we are here in terms of our water resources planning, that we have actually not a lot of idea what's going on, all this uncertainty, and that we are playing roulette. Fortunate, good news here is that's not the case, and that's what I want to talk to you about today, is the fact that we have a strong and a proven and a robust water resources planning environment. We use methodologies and software and modeling tools and so on that help us do this work. And it's based on a lot of good people that have done a lot of good work in the past. And here's just some of those names, and there are probably many names to add here. A lot of this is with support, particularly from the Department of Water and Sanitation, also the Water Research Commission and others. And I can, again, probably fill up this screen with millions of other logos and so on. And to a degree, all of us around the virtual table have made some sort of contribution. But I want to show you not all of these methodologies. I just want to show you some of them so that you have a feel for what it is that can and needs to be done when we talk about water resources planning, and particularly hopefully create with you an understanding of how important it is in your life and with regards to the sort of stuff that you do every day. So for starters, let's talk about the fundamental principles. So these fundamental principles, when I mention them here, is fundamental to the way to our approach in managing our water resources in South Africa specifically. But that doesn't mean that it's not done like this elsewhere. In fact, it is done like this in many other places. But South Africa has always been a little bit in the lead with all of this stuff because of the particular challenges that we have in managing our resources, as I mentioned earlier. So what are these fundamental principles? The first fundamental principle is that water users can be curtailed. What we mean by that is they are not fully supplied. Now, you might want to ask yourself, why is that a fundamental principle? Why can we say that? Why can we curtail users? I actually want to go one step further, which is to say we must make this statement. And the reason why we must make this statement is because runoff, rainfall, and the sources of our water in terms of surface water are fundamentally uncertain, as we've been discussing. So therefore, we cannot guarantee any user that they will always get all the water that they require. So we must make this statement. Now, if we accept that statement to be valid, it then takes us to the next fundamental principle, which is to say, because we know that curtailment is inevitable, we then prioritize users into different classes. For example, high, medium, high, and so forth, as you can see on the screen there. So we prioritize water use. We can probably have a whole discussion for 2 hours about how we do this prioritization. That in itself is pretty interesting. But fundamentally, it is based on the following. A water use would be prioritized as high if the implication of not supplying that water use, if it has a very significant socioeconomic impact, if we don't supply. That would then typically be prioritized as high as opposed to low. As an example, in domestic water use, high priority would be things like drinking, cooking, bathing, water that you need for those things. And low priority would be things like watering your garden and filling your swimming pool and washing your vehicle. You know, that's the sort of approach that we follow. So it's very important that we understand they are prioritized. Each system, you can go to the reports, each system has a priority classification like this. The Vaal has it, the Ngani has it, the Western Cape system, all of them have that. So once we understand that, the third principle is the following. This is very important. We curtail lower priority water use first. That makes sense, right? Why do we do that? To protect high priority water use. And that is the most, of the fundamental principles, that is the most important one, protect high priority water use. I'm just going to leave that on the screen for 2 seconds for you to have a look at and internalize these fundamental. You'll notice I don't have many bullet point slides, but I do have this one. Okay, so these are the fundamental principles then in terms of how much water we need, right? Here's an example of what that might look like, a priority classification table in an actual system. So here you have those classes I mentioned, high, medium, low, like that, right? So what we do is in every system, we have a classification table like this one, where we say, depending on which user type you are, your water requirement would be split into portions, and those portions are shown here. So for example, in this specific example, 63% of the domestic water requirement volume would sit under high, and 12% of that volume would sit under low. And for irrigation, you see irrigation has a different priority a different split into these priority classes, where most of the use sits in low and a smaller portion sits in high, and so forth. And you've also got some sort of split for the environment in this example. Now, all systems are unique and not all the tables look like this one. So just important to note, this is an example. For your interest, this example is from the Ngani system in KZN. So let's say these are, in this example of ours, let's say we've got these users and these are their requirements. This is the volume of water that they need. We can then use these percentages here to split that volume into smaller volumes under the different priority classes. So we would do it like that, for example. User 1, that's the split. These are the volumes required across those classes. Domestic user 2, irrigation, as we said, most of it sitting in low, an environment like that. Now, when we do planning, we go through this exercise, we take the volumes that we need and we split it across the priority classes. But then, very importantly, at the end, we add up the volumes. So we say, in high, I need a total of 58. In medium high, I need a total of 17. In medium low, I need a total of 8. And in low, I need a total of 17. All of that adding up to 100 in this example. Now, that stuff at the bottom, that represents in our system how much we need. Now, bringing it back to the scale, remember the scale where we had the how much you can get, the water source on the left, and how much we need we had on the right. That thing on the right is represented by this. These are the volumes of water that we need, our water requirement. And those would be in units, for example, like million cubic meters per annum or whatever the case is. I'm going to leave you just there for a second. We talked about the scale initially, and here we are showing a part of the scale, which is how much we need. And this is how we calculate those volumes across the different priority classes. So for the scale, let's say we know how much we need. The question then is, how much can we get? And that's what this next subsection is going to be about. Back to our little system here. Let's say we know that we want an abstraction there, but let's assume for a moment that there is some balance in storage here, a dam. Balancing storage would allow us to store water when there's excess flow, so that we can use the water in the periods where it's drier, in the dry season or the drier years. Let's say that is what we have here. Now, what we do in the water sources planning process is we tend to set up a lot of models. People often call me a modeler. I guess that's true to an extent, because we need to set these models up to be able to understand the behavior of things before we actually go out there into the world and build dams and operate dams and so on. We like to set up models because it's the appropriate place to do tests. Now, let's say in this particular example, we set up a model where we model the behavior of that dam, okay? This here would represent the full supply volume of that dam, and this would represent the dead storage volume of that dam. And we can then impose any abstraction volume on that dam in our model to see how the dam would behave, right, over a period of time. Now, let's say that abstraction volume, that's not the demand. It's just any abstraction volume that I pick. Now, let's say I pick a really small abstraction volume. Then I might be underutilizing the dam, and that might result in my model for the dam to behave like this. It will spill a lot of the time, and it won't really draw down very far. Now, that tells me something about this dam. If my abstraction volume that I picked is small and this happens, it suggests to me that the supply potential of this dam is higher. I can take more water out of this dam before I fully utilize the dam, right? So let's say I do this analysis in my model a second time, but using a bigger abstraction volume, then I might see a result that looks like this. And now I'm drawing my dam down more, but there's still some unutilized storage at the bottom here. So I might do a third analysis with an even bigger target. and that happens. You see where I'm going with this? So I'm starting to, in my model, achieve a situation where I'm fully utilizing this dam. Why do I want to fully utilize it? Because I want to see what is the potential of this dam to supply water, irrespective of how much we need. I've got that sitting on the side, but this is starting to tell me something about how much I can get. So let's say that this target draft results in it being drawn down fairly close to the dead storage volume here, but there's still a little bit of excess storage available. Let's say I increase the target abstraction even more, and that results in this sort of situation where the dam then actually reaches the dead storage volume, and I can no longer supply water from it. And this tells me that I'm now overutilizing this dam with this abstraction volume that I'm modeling. And I think you'll agree with me then that somewhere between this analysis with this target abstraction and this target abstraction, somewhere between these two, there is a very special target abstraction which results in this, where my dam once almost fails. So this target abstraction that results in this sort of situation in my model has a very special name, which is the historical firm yield. I'm sure that you've seen that name in many reports and whatnot. The historical firm yield is the biggest abstraction volume that I can impose on my dam without resulting in a supply failure. So it almost fails here, but it doesn't. That's called the historical firm yield. So you can see that's where it was spilling. Here's our near failure. And the period of time between those 2 points is referred to as the critical period. So the period in time, you can see in this particular example, if these are years, that's about 3 years is my critical period. Now, why is it interesting to know what the critical period is? The critical period in layman's terms, in the public domain, is also known as the worst drought. So for this specific modeled period of time, that yellow period represents the worst drought. Why is that important? Because this analysis tells us if our dam is big enough to bridge this period, to supply us over this period, it can also supply us over all of the other periods. That's why this is such a special period, this worst drought or critical period. While I use these words, you in your own mind might have a different definition of a drought. There are different types of drought. This is the most important drought from the perspective of water supply. So from a water sources perspective, this we would call the worst drought. Now, this is a very useful exercise because we can repeat this exercise. Let's say my dam here is a 1 MAR dam. What we mean by that is the dam size is equivalent to 1 year's worth of catchment runs. Let's say it's a 1 MAR dam. I will get a particular answer here. A specific target abstraction would result in this dam once almost failing. So the historical firm yield I can determine in this way for this specific dam size. But let's say I repeat this analysis for a bigger dam. You can imagine that a bigger dam will give me a little bit more water, even if it is subjected to this same worst drought. And likewise, if my dam is a lot smaller, then I would probably be able to abstract less water without causing a failure if it was subjected to this worst drought. So in this way, we can use the same model to analyze different dam sizes and determine different yields for those dam sizes. And I can plot those on a graph. Let me show you what I mean. So let's say this is my stream flow sequence. This is a specific catchment. I know what the monthly flows look like in million cubic meters. In this example, over a period of about 90 years or so, we're looking at the flows there. The average is plotted, and that's that little dashed line. I hope you can see it on the screen there. That's the average monthly flow. And you can quite clearly see, as for example before, the wet season and the dry season. So the seasonality is quite pronounced. But you can also see some dry seasons are wetter than others, And then I've got some sort of prolonged drier periods like I do at the end here, and so on. So that's what the flow sequence looks like. Now let's say I put this flow sequence in a model, and I define the size and shape of a dam also in this model, and I model the behavior of that dam over time, and I use the same analysis approach that I described before. I can determine the firm yield of that dam. And I can do the same thing for different dam sizes. And each dam size would give me a different yield. And we intuitively expect that the smaller the dam is, the smaller the firm yield would be, and the bigger the dam is, the bigger the firm yield would be. And indeed, if we analyze that system and plot, like I've done on the screen here, firm yield on the y-axis and the modeled storage capacity of my dam on the x-axis, then I might get results that look something like this. So for example, for a dam of 50 million cubic meters per annum, I get a yield of about 50. For a dam of 100 million, I get a yield of about 70 million cubic meters per annum, and so on. Now, yes, it's done what we expected. The yield goes up as dam size increases. What's really interesting for me, and this is something that is important to take note of, that there's clearly a difference when I look at what's happening for a small dam here, as opposed to what happens for bigger dam. Let me show you what I mean. If I increase my dam size from 0 by, let's call it 1 unit, I get a yield benefit of 1.3 units. Okay, but if I add 1 unit of storage here, I gain only 0.4 units of yield. That's really interesting. What you're seeing is this almost like a diminishing return on additional dam size when I express that in terms of yield. You see that? Quite clearly, this diminishing return, where ultimately it's capped by the amount of water that's available, right? So it can never be a straight line. It must always be diminishing in this way. That in itself is actually an interesting technical discussion. So we're not going to go there now. But if I actually connect the dots, as they say, then I typically see it exhibit this sort of curve shape. This is very common. They all look like this. Can you start seeing how this is useful to be able to help us when we're in a dam design, dam sizing exercise to pick the right dam size? I'm going to come back to that in a second. Okay, so with that in mind, let's look at some more examples. Let's say that the one that you just looked at is catchment 1. There it is, plotted like we did before. But let's say we have another catchment, or catchment 2, the green catchment. Yeah, catchment 2 looks like that. This is also flows plotted in the green catchment, and you can see that they look very different. So I'm just going to toggle between the two. Yes, I see there's a question there, Ashley.
Sorry, it's not time for question and answers yet, but the hand looks like it's been lowered. Gerald, I think just continue.
Sorry, I'm just trying to, just give me a moment. Say it again.
You can just continue. The person has lowered their hand.
Actually, no, sorry, man. I couldn't get that.
Please continue. The person has lowered their hand.
Okay, thanks. Okay, so I'm going to toggle between these two. That's catchment 1 and catchment 2, and you can clearly see how different they are, right? These are monthly flows at the outlets of these catchments. So catchment 1 and catchment 2. Now, the very important difference that you see here is that this catchment 2 is quite clearly more variable than catchment 1. Catchment 2 more variable than 1. But in addition to that, they have the same average. So the average is exactly the same. The only difference is that catchment 2 not the only difference, but the difference is that catchment 2 is more variable. Okay, I'm going to show you a third catchment, catchment 3, and that one is almost is even more variable than catchment 2, but again the same average. Okay, let's look at all of them. Catchment 1, 2, and 3. So the catchment 1 is the least variable, more variable, and even more variable, but all of them have the same average. What's really interesting is if you take these 3 catchments and you do the same analysis on all 3 of them by testing different dam sizes, determining the firm yield for each of those, and plotting it on a curve set, you've seen catchment 1. That's the result for catchment 1 that you've seen already. But watch this. If I plot the results for catchment 2 and catchment 3, which are more variable than catchment 1, we see this interesting thing happen. For the same dam size, we get not just less yield, significantly less yield. For example, for this dam here, the 100 million cubic meters dam, if I build a dam of that size in catchment 1, I'll get a yield of about 70. If I build the same dam size in the other catchment, I'll get a yield of only 50. And in this one, a yield of only 30. So what I'm trying to illustrate to you here is another very important concept, which is the fact, remember I said before, you can't just look at averages because that's wrong. This also illustrates that average is important, but equally important, as you can see here, is how variable the hydrology is. The more variable it is, by rule, the less yield you will get for the same size dam. And you can see that on this graph here. These are very typical. You might be interested to know, just to put this into some perspective for you, what catchments these are. These are real catchments. We just scaled them to have the same average. But this blue catchment is upstream of Vaal Dam. Sorry, no, apologies. The blue catchment is Midmar Dam. The green catchment is Vaal Dam. And the red catchment at the bottom here is the Fish River in Namibia. You can see how massively different they are from a yield perspective. Now, what we ideally want to do if we design dams, if we can, it's good to have them in catchments that look a little bit like a blue well, because we can get a lot of yield for the same size dam. But in addition to that, also, we really want to try and build dams purely from a water sources perspective on this side of the curves, where I get a lot of benefit in yield for every storage size. The further along I move to this side of the curve, the less benefit I get for increasing the size of the dam. Having said that, we don't only look at that as a consideration. We obviously look at what the actual demand is. There's no point in building a small dam because we want it on the side of the curve, but we can't supply the demand. So the demand in itself is a big driver of sizing dams, and so is the cost. So we look at things like unit reference values that account for both yield and the cost of constructing the dam in question and so on. So it becomes particularly complicated from that perspective. But this certainly is a very important component of dam sizing. I want to show you as an example what that might look like. So, oh, by the way, sorry, these curve sets are when we ignore evaporation from the dam. A similar curve set generated in exactly the same way, but now accounting for evaporation, and you can see the impact of evaporation. This is without evaporation, and this is with evaporation. It's a massive impact. And sadly, and you'll know this, I think from experience, is in these arid catchments where I don't get a lot of yield to start off with, they also tend to be, in South Africa at least, in warmer places with higher evaporation. So it's sort of a double whammy in terms of moving from the blue to the red like this in the catchment that you are, in the sense that you don't get as much yield there because of these two dynamics working together. I'm going to show you again. It's quite interesting. So this is without evaporation, and this is with evaporation. Just to be clear, I'm talking about the evaporation from the surface of the dam. So evaporation losses from the dam itself. Now, in terms of using this for dam sizing, I did touch on that a little bit, but let's say, for example, that I need a yield of 50 million cubic meters per annum. So this is my target. This curve set is really useful because it shows me what sort of dam size I need. And let's say I'm working in the blue catchment. This tells me that I need a dam of about 55 or so million cubic meters to be able to give me that yield in the blue catchment. But then you'll see here that if I have the same target, but I'm actually sitting in the green catchment, I need a dam that is significantly bigger than that to give me the same yield. This dam is almost more than 3 times the size of the dam I would have needed to develop in the blue catchment. Isn't that amazing? I think this graph and looking at it like this is pretty insightful. I don't know what you'd do if you were sitting in the red catchment, because you'll probably never be able to get that yield in this catchment at all. When you consider evaporation like this, I mean, the bigger the dam becomes, in all seriousness, if you were in this red catchment or even in the green one, and you're looking at these sorts of yields, you might want to look at alternative options because you're starting to build a dam that's so big, the evaporation losses become so large that they tend to outweigh the benefit of increasing the dam size. You're effectively building an evaporation pond rather than an actual water supply dam. So how do we get around that? I wanted to ask you, Ashley, where we are in terms of time, and whether we can cover part of this aspect here as well.
Gerald, it's now 3 minutes till 4, but you are still welcome to go on for another, I think about 20 minutes before we need to move on to questions. Yeah.
Okay, perfect. Thanks a lot. Okay, so we're doing well. Thanks for that, Ashley. So now with all of that having been said, I spoke about risk, I spoke about uncertainty. The key here in the water sources environment and how we do planning in this country is we don't ignore the risk or use safety factors or things like this. We go in and deliberately try and manage this risk. How do we know it works? Because we've been doing it for 40 years. It's been tested and tried, and we manage all our water sources systems in this country, at least the major ones, we manage using these principles. So I'm going to explain those principles to you here. What we've been looking at so far is analyzing the historical hydrology. So the flows that did happen in the catchment, we've been looking at those flows driven by the rainfall that did happen in those catchments, right? But let me explain how we then take that information, these principles, and how we use it to manage risk. Now, you will remember the fundamental principles slide where we said we can curtail, we prioritize, and we curtail low priority first to protect high priority water use. Those were the fundamental principles. But how do we actually practically do that in systems? Well, what we do is we add this final one, which is to say, we develop criteria based on risk, specifically the risk of not supplying the water requirement, not supplying the demand. That we set as a criteria. Let me show you, this is just an example, right? Every system has unique ones, but let's say, for example, we've got priority classes called high, medium, low, and low, like we said before. What we then do in every system is we define the risk criteria associated with those classes. So what is the acceptable recurrence interval of not supplying? And we generally define those in years, like I've said over here. So what is the recurrence interval of non-supply under each of these? So in this case, high is 1 in 200 years. So once every 200 years, on average, I will not be able to supply the full high requirement, that water use under high. And once every 100 years, will not be able to fully supply medium high. And you can see that the lower the priority, the more frequent the supply failures may be. We allow this to happen. We plan for this to happen. We plan for droughts because then we know they will be there, but we limit the risk based on these criteria. Does that make sense? So we express those generally in recurrence interval of failure. That's the top line. And then you can express the same recurrence interval of failure as an annual risk of non-supply, which in this case is 5%. How do we calculate the 5%? It's 1 over 20. So the probability of not fully supplying the low priority use in any given year is 5%. And by virtue of that, the annual assurance is 95%. And you can see this assurance, this annual assurance of supply increase as we move from low priority through to high priority, with the understanding that this represents, in terms of water requirement, how sure we want to be that we get that water. And with the additional understanding that if there's not enough for everyone, we will start curtailing low first. And only when low is fully curtailed will we start curtailing medium low, and so on. Do you see? So that we protect the higher priority use components in this methodology. That makes sense. Now, how does that relate to what we spoke about before? Do you remember this table where we said, okay, we've got 4 users and this is their requirement. And this at the bottom here represents how much we need. 17 in low, 18 medium low, and so on, up to 58 in high. That totals 100. What we would then typically do in this on this sort of table, this priority classification table, is we would add the risk criteria. So we want this high portion, this volume, we want at 1 and 200. And this portion, we want at 1 and 100, and so on. Okay? This here represents how much we need and at what recurrence interval of failure. All of those adding up to a total of 100. So again, think back on the scale that we spoke about. This here represents how much we need. Now, I spoke in the earlier section about how much we can get, but analyzing the historical hydrology. Now, the problem with just doing that, and this is another thing that I wanted to mention today because it's so very important, is yes, we use the historical hydrology to develop for ourselves an understanding of the supply potential of a dam, the system of dams. What is the supply potential or the yield of that dam? But let's say this is the historical hydrology. And I mentioned this before. If I had data only up to here, let's say this is today, and I have data for the past 10 years or the past 100 years, but I don't yet have data for the future because it hasn't happened yet. And I also don't know what it's going to look like. I think you'll agree that if I could plot the next 10 years, it will have the same look and feel as the earlier 10 years, assuming there's no climate change. It will have the same look and feel, but it wouldn't look exactly like this. I might not have as wet a year as this one. I might have a more severe dry period than this one. I don't know. And that is the problem. In that sits that very fundamental uncertainty is I don't know what future flows, future rainfall and future flows are going to look like. And again, for the moment, ignore climate change. Even without that, we don't know what they're going to look like. It is fundamentally uncertain. So because of that, we developed a methodology in South Africa, and it's not unique to us. Other countries use it too, but we've developed a methodology that's based on stochastic hydrology. So we've got the historical hydrology, but we can generate stochastic hydrology. What on earth does that mean? I don't want to take you through a lesson on statistics because everybody will fall asleep, right? But basically, stochastic hydrology is what it says here on the screen. We develop hydrological sequences synthetically. What we mean by synthetically is they didn't actually happen. They may never happen. We generate these hydrologies in a computer using statistics and using calculation methods. So they didn't really happen. They won't ever happen probably. But if any one of these sequences did happen, it would not be out of place. What I mean by that is they could happen. They're plausible sequences. Now, some sequences are wetter than others, some are a bit drier than others, some have wetter periods, some have maybe slightly drier periods and so on, but any one of them is equally likely in our catchment. We use the historical hydrology as a guide. And then we fit statistical distributions and we use special software to generate these stochastic sequences. And we can generate many of them, however many we like, 10 or 1,000 or whatever. And what we do then is we say, instead of analyzing only the one historical sequence, we can, in the same way, analyze many stochastic sequences so that we ultimately end up with all possible outcomes, if that makes sense. Rather than just the one outcome, we have many outcomes. Some of them can be less favorable, some of them can be more favorable, some can be more middle of the road. But at least we've analyzed an entire set of all possible outcomes. Now, you might ask me, how do you know that it represents all possible outcomes? These stochastic sequences aren't perfect. We all know that, and it's still somewhat of a guess. But at least what we're doing is we analyze so many sequences so that up to a point we get to a situation where even if we add more stochastic sequences, our results start to stabilize, right? And this has been tested as part of postgraduate studies and so on. So we know how many sequences we must analyze until we get to a reasonable answer. Now, if we do this, if we generate sequences like this, they look, why I show you this is because I was wondering, what do these stochastic sequences actually look like? This is just to give you a feel for it. This is Vaal Dam, and this here is the actual historical sequence of flows for that dam. These other three have been generated using a machine. They never actually happened. These are synthetic sequences. So this is not particularly scientific, what I'm saying now, but comparing them, you can see that they have the same, sort of generally the same feel, although they don't look the same. Each one of these is unique. Similarly, if I show you Katse Dam, one of the sequences that I'm showing you here doesn't fit. I'm going to give you a few seconds to look at these plots and see if you can find the one that doesn't fit. If you pick number 3, you were right. How did we know it was number 3? Well, it's clearly more variable than the others. And in fact, this one doesn't fit. This is the stochastic sequence 1, stochastic 40, stochastic 101 for Katse. This one here was just copied from Vaal. It's not even the same catchment. But you can quite clearly pick up the fact that it doesn't quite fit the others. What I'm trying to suggest to you is that we want to create stochastic sequences that are feasible for that particular catchment, so that we can believe that that particular sequence of hydrology could happen, so that we can then use it in our analyses. Every sequence is equally likely, every sequence is feasible. Now, using that, instead of then having a roulette wheel where we don't know where it's going to fall, instead of guessing where it's going to fall or trying to predict where it will fall, I cover all options, or all possible outcomes. Does that make sense? So it's no longer gambling, it's planning. Now, without going into the details, considering time constraints, how we generate a graph like this, what this stochastic analysis, stochastic yield analysis, the outcomes of that is this result. It's called the yield reliability curve, or YRC. What we're looking at is yield on the y-axis and sort of an assurance and supply indicator on the x-axis. But what we actually plot on there that helps us guide things is the standard recurrence intervals of failure. So you can see there's 1 in 200, 1 in 100, 1 in 50, and 1 in 20 in this case. Now, we talked about how much we need, right? This curve set represents how much we can get. What yield can we get at different recurrence intervals of failure? So thinking back on the scale, this is the thing on the left-hand side, how much we can get. And what we need to do now is compare how much we can get, this graph, with how much we need. Let me show you how we do that. It's pretty neat. Here's our example. We need this much, a total of 100 million cubic meters per annum, 58 on high, 17, 8, and 17 across those recurrence intervals. Now, what we do is we take these numbers, if you can try and sort of remember these numbers. First of all, we must understand what the total is. And then we must plot these demands on the curve set. Let me show you how that's done. Here's the curve set. First of all, I highlight the line that corresponds to the total requirement of 100. Let me show you that again. This is without it highlighted. Why 100? Because that's the total demand. Yeah. Okay, so I go to the curve set, I find 100 on here, and I highlight the line that corresponds to that demand like this. That is how much we can get. And then I plot on top of that how much we need. It's 58 at 1 in 200. You see it's on the 1 in 200 line. Yes. An additional 17 at 1 in 100, 8 at 1 in 50, and 17 at 1 in 20, like that. That represents how much we need. And this is the scales in action, comparing how much we need, which is the bars, to how much we can get, which is the blue line. And if the bars are not above, the blue line, then the system is in balance. Let me show you a random second example. So this is just confirming we have actually now done this. Shown you how to do this in reality. Actually, can you just give me a thumbs up to tell me that you guys can still hear me?
Yes, I can hear you.
Good. Okay, fantastic. All right, let me show you. I'm just going to show you two more random examples, and then we're going to be just about there to take some questions at the end. So here's a random other example. In this case, we've got requirements for different types of users. Here are the priority. Here's the risk of non-supply, recurrence interval non-supply criteria. The requirement volumes adding up to a requirement of 50. Now, it's exactly the same sort of procedure. Here's the YRC. The first step is to say, what's the total requirement? It's 50. So I need to pick that 50 and highlight the corresponding line, which is this line. Okay. So that represents how much we can get. And then I must plot these requirements, these requirement volumes onto the same curve set like that. And you can see that in this case as well, these bars are how much I need. The blue is how much I can get. And in all cases, the bars are not above the blue line. And that means that this system here is also in balance. And a final example, it's exactly the same thing. But what we've done is we've now moved the the industrial from 1 in 50 to 100. Let's say we decided that these users must be supplied with a higher assurance supply. So we've moved that into 1 in 100 as well. So now we've got 20 in 1 in 100. So it's 15, 20 there, and 15, still adding up to 50. So here's the curve set. Again, I must pick the right line. So 50 there, highlight the line like this. And I plotted, and you can see quite clearly now that now this bar sticks out above the blue line. And that means that what we need is more than what we can get at 1 in 100. That there is called the violation. The system is not in balance. So what that actually means in practice is if we run the system like this, if we do nothing, then this volume, this portion that's plotting above the blue line will in fact actually be supplied at a lower assurance, whether we want that or not. That is just going to happen. So this is what will happen if we run it and do nothing, just allow it to supply as is. We will lose assurance of supply here. And you can see that if we allow this to happen, we're actually violating one of our basic principles, because we are lowering the assurance of supply on a high priority user while not cutting back on low priority use. Do you see that? Low priority use stays unaffected. So this is actually not what we want. What we want is a different approach where we cut back on low to protect high. That's what we said that the fundamental principle is. So let me show you how we do that. Instead of using, remember we use this curve, right? This blue curve, because that adds up to a 50. We say, let's allow a reduction in supply. And how we do that is we actually pick a different curve. Instead of the blue curve, we pick our own curve. What curve do we pick? One where there is not a violation here. You see, we've resolved the violation on medium high. But as a result of that, overall, we can supply a little bit less water. Do you see the little shortfall here? But now the shortfall is sitting on low, which is what we want. So we're cutting back on low to protect high. In this case, there's a shortfall of about 2 million cubic meters per annum, which means that instead of allocating 50 million cubic meters per annum, we can allocate only 48. And this is how we use this methodology to also help us understand how much water we can allocate from a given system. This is very, very valuable. So in summary then, I think in terms of time, hopefully, actually we're doing pretty good. And I'm hoping for a lot of questions. So there's some time for that. To summarize what we discussed, we spoke at length about uncertainty, how uncertainty is fundamental to the challenge we have in the water resources planning environment. Why is that uncertainty there? Because rainfall is fundamentally uncertain. We don't know what rainfall is going to look like in over any future given period of time. If we added to all of this climate change, that makes things even more uncertain than it currently is. So very, very uncertain, this environment. The second principle is that, or the second thing that we spoke about is this idea that we prioritize water use and that we manage our systems to cut back on low priority use for the purpose of protecting high priority use. We then spoke about how much we can get. We looked at two basic methodologies. The one methodology is based on the historical yield that gives us firm yield numbers, which is an indication of supply potential of dams and systems, but then that we actually can't use only that because the historical hydrology will never happen again. So what we then do is we use stochastics to actually quantify assurances of supply, so how much we can get and at what assurance, and then we compare that to how much we need at different assurances to see whether our systems are in balance or whether we have to cut back on how much water we can allocate from our systems. And in that way, we go and deliberately and proactively manage the risk, that same risk that is introduced by the uncertainty that we spoke about before. And in essence, ladies and gentlemen, that is what I wanted to share with you today. I'm hoping that was interesting, and I'm also hoping that there's a lot of questions and a bit of discussion around that. Ashley, thanks.
Thank you so much, Gerald. We really appreciate your time and for going into so much detail. I think it was really interesting, and I wish there was more time to explore some of those additional aspects. But yes, I would like to open the floor to some questions or some comments. Just to answer the person in the chat, yes, the recording will be made available probably sometime tomorrow in the chat on Teams, but you can also find it on LinkedIn. Okay, so if you have a question, please raise your hand and then I'll give you an opportunity to speak. All right, Alan, you can unmute yourself and ask your question.
Thanks, Ashley. Thanks very much, Gerald. That was excellent. This is not a question, it's a comment. When I was with the department in 1986 and in the planning branch, it was sort of, this sort of affects water resources. You might remember the figure from your side. In South Africa, we lose one sizable dam. I won't give you the number in storage capacity. We lose one sizable dam per year. And secondly, for all the major dams belonging to the department, the really big one, well, most of them, each one has a recurrence interval of having a bathymetric survey done on them to see, and that could be 8, 10 or 15 years to see what storage capacity has been lost to put into their overall water resources management model. Can you please expand on that?
Alan, yeah, I mean, that's so important. I'm really glad you mentioned this today. Let me start off by saying this: the sorts of requirements and bathymetric surveys that you mentioned there, and how important that is, and I can't agree more. And they don't happen often enough. And I can think of many examples where we anticipate that a lot of sediment deposition has happened in the dam basin, but we don't know the numbers because we don't have bathymetric surveys, and that results in us having to make assumptions about what those are based on modeling and so on. And even if we know what the loads are, we don't necessarily know where that water is going, where the silt is going to deposit in the dam basin. And so that poses an enormous challenge to us in the planning environment. So it implies making assumptions which are not ideal. But what I can say on the positive side, apart from that, is that we do have the modeling tools, fortunately, that allows us to quantify the impact of sediment on yield, and also allows us to test operational measures and the impacts of those on losses and system yields as well. So the tools are there, but the challenge is significant.
Thanks very much.
Kevin, you can unmute yourself and ask your question.
Afternoon, everyone. Thanks, Gerald. It's very interesting talk. I was wondering, I may have missed this, but when you were speaking about the stochastic sequencing, you mentioned that you can run, if you run enough models, you tend to get a stabilization of the results. Obviously, if you're doing lots of scenarios and you've got limitation on time, the more simulations or sequences you run, the longer the simulation takes, and it comes down to processing powers and whatnot. So the question is, typically, how many stochastic sequences do you target to get a reasonable stabilization when it comes to stochastic modeling?
That's a really good question, Kevin. Thanks. And again, glad you asked that. I would like to talk about that quite a bit if I have the opportunity. And I think we need to create opportunities to delve into that a bit more. We apply some basic standards in the modeling that we do, which is based on, as I said, research has been done in the past to come up with these numbers, but I wasn't involved in it a while ago, and there might be an opportunity or the need to go back into that again and test a number of sequences on outcomes that we get. Having said that, the standards, which I think you're after, is when we do long-term stochastic yield analysis, so we're analyzing a system over 50, 60, 70, 80 years or whatever, we run that system stochastically. The industry standard, if you like, for that sort of analysis is 201 sequences. The and one at the end isn't because it, often joke to say it makes us sound clever and we really thought about it, but the and one is so that you have an odd number and that a particular sequence represents the median. So 201 is pretty much the standard. If you do short-term analysis, you tend to want to have more sequences to give you more data points to be able to extract statistics out of that. And the standard for a short-term yield analysis, short-term would be 5 years or so, would be 501 sequences. Kevin, I hope that helps you. You did also mention processing time. The models that we currently use as a standard run on your desktop. So they're dependent on your CPU and your RAM. We are working very actively away from that to a system where everybody can run their models in the cloud, that presents massive advantages, one of which is being able to use the computing power that's available there by using virtual CPUs and the like at very reasonable costs, actually. So that's the way that the world is moving, and that will ultimately allow us, for example, we currently run the integrated file river system in something called the planning model, and that takes a day to run for a scenario. We can probably reduce that computing time by orders of magnitude if we ran the same system in the cloud and paid a small amount of money to be able to do that. So Kevin, that's where we're moving. I hope that's good news.
Thanks so much.
Edwin, you can unmute yourself and ask your question.
Thanks, Gerald. Just I was wondering, what's the minimum one's expected to do these days regarding climate change? And
yeah,
with your sort of, that's a difficult question, but also on the studies and what you know, what's our future looking like in terms of climate change? What is, we know the sedimentation is impacting us heavily, but what's climate change going to do?
Always with the difficult questions, Edwin, but thanks, it's good. So in terms of climate change, where we currently stand, and I've been saying this like many years and over again, is like we really don't know where we're going. If you investigate and you interact with the climate modelers and the guys that understand that stuff better than you and I do, the constant message seems to be that, and it's sort of understandable, is the outcome that you get from a climate model is dependent on many things, but largely which climate model you use, which downscaling methodology you use. Downscaling is to get it from the regional and global scale down to where you are in water catchment. That methodology has a big impact, and also which CO2 emission scenario you pick. There's standard CO2 emission scenarios that have been defined and published by the IPCC, and you can go look at those. But those vary massively, and that also is understandable because you don't know what future policy is going to look like, and you don't know what future geopolitics is going to do to the way that people behave, and those uncertainties sit there. Unfortunately, downstream of that, when we use these things and we pick our scenarios and whatnot, we also come up with vastly different answers depending on which one we pick. So in this chaos, we sort of agreed that we would favor certain specific IPCC scenarios. The one being the, if you like, middle of the road, one being the do nothing and things just get worse, and the one being an optimistic one. So at least you've got a bit of an envelope of where things might land and plan according to that. If you are interested in more details around this, there's a currently study being undertaken for the Department of Water and Sanitation by various of our colleagues. James Cullis is involved. He's the man as far as climate change is concerned. As part of that, he's developing a standard, if you like, simplified methodology for us to be able to follow in the planning process, where it's recommended to use these three scenarios, as I mentioned, and this is how you would go and apply it, which Edwin just very simply means that we take the output from the climate models, specifically potential evaporation and rainfall, we apply it to, in our rainfall runoff model, we generate new runoffs, and then we take all of that stuff and build it into our yield models and planning models to model the impacts. But we still end up with 3 answers instead of 1, or 50 answers, depending on how many scenarios. Edwin, sorry, I hope that's a vague answer, but it's a vague thing, so are you happy with that?
Are there any other burning questions? If I can ask a short question, Gerald. You mentioned that your work is highly dependent on rainfall gauging. I just want to know how dependent is your work on gauging stations, specifically the data that's generated from them.
You mean streamflow gauging?
Yes. Sorry.
Okay, thanks. Actually, so let me quickly touch on both of those because they're both very important because of the same reason. Other reasons too, but very basically, we use rainfall data when we set up our rainfall runoff models. Okay, and once we've set up a rainfall runoff model, we still don't understand the rainfall runoff response of a particular catchment. Each catchment has a unique hydrological response. And that's why the streamflow data that we monitor is so very crucial. Is we set up our model, we've got rainfall historical, we put it in there, but then we need to be able to calibrate our model, and we calibrate it against the observed streamflows. Once we get a good calibration, then we know we've got a good rainfall runoff model, and then we can use that model to generate, to simulate streamflows over a period where we don't have gauging. But ultimately, we can do none of this if we don't have the gauge data. So as much as we need good rainfall data, we also need good streamflow data. We're very fortunate, I have to just add, in this country that we've got generally quite good streamflow data. And also, and you'll be surprised maybe at the statement, but that streamflow data is readily and freely available online. You can go to the DWS website and download daily streamflow data right now. It's there. That's not the case necessarily in other countries, so we're thankful for that.
All right, thank you. I really appreciate that. I just want to check in the chat. There was something that came up. Okay, it's just a thank you. Yes, so I just want to also thank you, Gerald, so much for coming out and being open to the questions and for responding so well. And also, we hope that we will be able to continue some of these conversations at different webinars later on. Yes, thank you so much. I'm going to take 2 minutes just to advertise for SANCOLD. So if you are not a member, you can become a member by going to our website and click on the Become a Member button and then fill in the form and follow the steps and register. It's one of the cheaper voluntary associations you can be part of. And if you didn't know, if you are a full-time student, membership is free. So please take that opportunity to become a member and be part of our community. Furthermore, we have a iCourse short course coming up next week from the 4th to the 5th of November on slope stability, specifically for tailings dams. And then I think you can still register for that on the website. Same for the conference, which is just after that. It's from the 6th to the 7th of November at the Wanderers Club in Johannesburg, and you're also welcome to register for that. You'll have 1 CPD credit per day. If you attend both days, you'll have 2. So that's quite a lot. Okay, thank you so much.